Hello everyone, welcome to this presentation. My name is Naresh Kumar Inna. I am co-founder at a startup called MemHive, where we accelerate applications using persistent memory. We have chosen the popular open source database Postgres as our pilot application, and that is going to be the subject of our presentation today, which I will jointly present with my co-founder Keshav. Here is the agenda of today's presentation. We start off by looking at various ways of using PMEM for databases. We will then take a look at the storage architecture of Postgres, where we will discuss how the cache, the write-ahead log, and the relational data is laid out. Next, we will look at how MemHive scales Postgres with persistent memory. After that, my co-presenter Keshav will walk us through some benchmark numbers achieved through the scaling with PMEM. And finally, we will wrap it up with some conclusions. Persistent memory, as we know, is a layer that sits between fast SSDs and DRAM in the storage memory hierarchy, both from a performance as well as cost perspective. Low latency and large capacity are two distinct characteristics of PMEM that make it very attractive for memory-hungry applications. Meanwhile, with the exponential growth of data, databases are being stressed beyond their abilities as they attempt to vertically scale with their traditional storage architecture, which is primarily designed for fast volatile DRAM and slow persistent disk storage. PMEM attempts to bridge these gaps and hence is seen as an ideal solution to solve the database scaling problem. Databases have already started integrating PMEM into their storage stack. Let us look at some of the ways they've been doing it. As most of us may already know, databases use a method called transactional logging to quickly acknowledge client-side inserts or updates before committing them to their final stable storage location. They're known as write-ahead log in Postgres. They're also known as redo log in some databases or append-only files in Redis and so on and so forth. Storing the logs on PMEM is one of the most common use cases for the obvious benefit of speeding up writes. Using PMEM to store cache data as opposed to using DRAM is another use case. PMEM could also be used as a cache tier. The persistence of PMEM can also be put to good use by hosting the entire database itself on PMEM, turning it into a large in-memory store. Next, we have the two conflicting modes of PMEM usage. Databases could transparently use PMEM in memory mode as a large cache, although it may not be the most efficient use of PMEM since it is volatile and the application has no control over the caching mechanism. The more efficient app-direct mode can be used instead to take advantage of persistence and performance. We will see how we do that in the slides that will follow. Now, let's take a look at the storage architecture of Postgres. It follows a traditional model that is designed for a combination of fast DRAM and slow disks. The Postgres cache resides on a memory mapped region of DRAM and hence is volatile in nature. We will look into this later into this layer in the next slide. Postgres lays out its storage as files on a traditional file system like ext4, XFS, or NTFS. They could be used for storing the write-ahead log, the relational tables, indexes, the commit log, free space maps, visibility maps, and so on and so forth. This is the high-level architecture of the Postgres cache, which is also called the shared buffer cache to those of us who are familiar with Postgres. Shared due to the fact that it is actually shared between the server's processes. It is created from a single memory mapped region of the kernel page cache, which resides on DRAM. When a server backend process needs a buffer from the cache, it provides something called a buffer tag to the buffer manager, which is a shorthand way of identifying a page that the buffer maps to in the relation file. In other words, a tag is a tuple made up of the object IDs of the table space, database, and the relation, which is known as which is together known as the relation file node. When combined with the block number, it is used to find a page in the relation file. In response, the buffer manager provides the process a buffer ID to identify the buffer. Let's now take a look at how the buffer manager itself is organized. Uh, it's organized into it's a three-layer buffer manager. The first layer is the buffer table, which is nothing but a hash table that maps the buffer tag to a buffer ID. The buffer ID is nothing but an index into an array of buffer descriptors. Uh, each buffer descriptor points to its corresponding buffer. The descriptor also has the state of the buffer and has links to the free list chain among other fields. The buffer layer is a contiguous array of fixed size buffers, typically 8K, which is the page size of Postgres. Each buffer holds an exact copy of the page in the relation file. Now, let's now take a look at how memhive scales Postgres with PMEM. Before we actually jump into the architecture, let's first take a look at some of the things that one has to consider when choosing PMEM for Postgres. Firstly, the choice of the API to talk to PMEM, which is either libpmem or libpmem obj. Using the PMEM obj library poses some challenges with Postgres. Unlike a DB like MySQL or MariaDB, Postgres doesn't provide a storage engine that is pluggable, has a well-documented API, and can be used to intercept IOs and redirect them to the PMEM obj library in order to use its transactional API. Using the transactional API in existing Postgres IO paths itself would lead to significant rewrite of those paths. Whereas using the more low-level libpmem API would allow us to more easily modify Postgres storage paths without changing its design. Given that FSDAX namespaces cannot be used to create LVM mirrored volumes, using libpmem would mean not having redundancy against events like local PMEM DIM failures, as against using libpmem obj pool sets. This is a critical requirement for hosting the write-ahead log or the database relation files on PMEM. The next consideration is of the effects of non-uniform memory access, which is more pronounced with PMEM, given that it has to flush and drain for power fail safety. This is more of a consideration for deploying workloads on PMEM as against designing applications. Here is a look at memhive's Postgres architecture. It provides the following features: a PMEM-based persistent cache for buffers, storing val files on PMEM, storing the DB files on PMEM, and a manager that helps in provisioning and monitoring PMEM for Postgres. Let's start by taking a look at the persistent cache. So what is it? As the name suggests, it is a non-volatile cache residing entirely on PMEM, which means that the contents of the cache are preserved across restarts of the server or restarts of the system. How do we do that? Two of the layers of the buffer manager will now reside on PMEM. The buffer descriptors and the buffers themselves are mapped to files on a DAX-mounted file system. Since the cache is persistent, it needs to be fail-safe atomic. We introduce cache flushes and batch drains at critical points in the cache manager, using both the more efficient PMEM copy no drain API, or where we have to write the cache data or the metadata, we actually issue a PMEM flush followed by a PMEM drain. In addition, during the when the Postgres server initializes itself after a planned or an unplanned restart, we ensure that buffers which are either unused or are not guaranteed to be committed to persistent memory are moved to the free list, while the rest of the buffers are left intact. In the normal case, all the buffers would be moved to the free list. There are two modes of persisting the cache. The first mode is where the buffers are always guaranteed to be persistent, even across unplanned restarts of the server, like crashes or power failures. In this mode, we ensure that the buffer contents and critical buffer fields, descriptor fields, are flushed and drained from the CPU caches for persistence. The second mode is where we save the penalty of flushing and draining the buffer and the metadata updates, although this penalty was found to be minimal during the benchmark tests. Uh, Obviously, this mode will work only for planned server restarts. Memhive Postgres also has an optimization to avoid persisting buffers from operations such as vacuum or bulk writes, which result from copy-in operations. These operations use a very small ring of buffers that are overwritten frequently. Moreover, flushing and draining these buffers can increase the time to complete these operations. The next feature is about placing the write-ahead log files on PMEM. This can be done in two ways. A performance mode, which places the write-ahead log files on a DAX-mounted file system and uses the PMEM memcopy API instead of the POSIX write API in the POSIX in the Postgres path that flushes the in-memory write-ahead log buffers to stable storage. Then we have a local redundancy mode that uses a file system mounted on a LVM mirror made up of sector mode namespaces. This comes at the cost of slightly reduced performance. Lastly, if the size of the database, which is basically the table and the index files, can all fit into an LVM mirror device made up of sector mode PMEM namespaces, one could use that option while the cache remains on DRAM. As mentioned earlier, usage of sector mode comes at the cost of reduced performance with the trade-off of having local redundancy. Talking of redundancy, one could use libpmem with either of FSDAX or sector mode and back up the database to a remote server using the existing Postgres replication techniques. With the features we described, the following configurations of using PMEM with Postgres are possible. A configuration where PMEM can be used as a persistent buffer cache and for storing the write-ahead log. In this configuration, we can have a local redundancy mode or a performance mode. The local redundancy mode combines DAX and sector mode namespaces. While we use the DAX namespace for the cache, we could have the write-ahead log on a LVM mirror made up of sector mode namespaces. This would require us to have non-interleaved PMEM names. And then there is the performance mode, which will have where we will have DAX namespaces created on interleaved PMEM DIM regions for hosting both the write-ahead log and the cache. In this mode, the relational data files will continue being stored on their existing storage, which could either be direct attached or SAM. The second configuration is where the entire DB can be placed in persistent memory. Again, we have a local redundancy mode in this configuration, which will use only sector mode namespaces, creating an LVM mirror to store the write-ahead log and the relational data files. A performance mode where the relational data files are stored on sector mode namespaces, while the write-ahead log will be stored on a FSDAX namespace. In this configuration, the shared buffer cache is unchanged and will remain on DRAM. Here is a look at how Postgres lays out its files in its data directory. On the left is a listing from a standard Postgres installation. On the right is how memhive Postgres places the write-ahead log and the persistent cache on a DAX-mounted path. My co-presenter Keshav will now walk us through some benchmarks. Over to you, Keshav.
Thank you, Naresh. Hi all. I am Keshav Prasad, one of the co-founders at memhive. Today, I'm going to continue this presentation and talk about the various tests that we have done and benchmarks that we have done with memhive Postgres along with persistent memory. And I'm going to show you various metrics and the results that we have obtained, which tell us clearly how great the performance of persistent memory and Postgres that we have achieved at memhive is. Next slide, Harish. All right, before I start off with the test configurations and the test server itself, I would like to mention that we have been with a partnership with Intel, which has graciously sponsored us a server in their SDP cloud, which has all the necessary things for us to test Postgres and our various features that we have developed on top of Postgres. And the hardware that we have used is called Intel Optin. There are many PMEM options, really speaking. There are many providers for persistent memory as well. But the leader in this technology has been Intel, and it's called Intel Optin. It is having the best performance as well as the scalability in terms of size compared to other vendors. So using Optin PMEM, we are able to scale Postgres in a vertical manner. Now, let me talk about the test environment. As I was talking about, Intel has provided us one of the servers in their cloud, which is having 2 sockets with 24 cores in each of the, each processor having 24 cores, 1 in each socket. And each socket has been populated with memory banks, both with DRAM as well as persistent memory. DRAM, we have 16 GB modules on 6 on one side and 6 on the other socket. Similarly, with persistent memory, we have 128 gigabytes of Optin, populated 6 per socket. Now, at this point, I would like to mention one more important Intel is that the Intel scalable family Optin, and that has of having 128 gigabytes modules starting at 128 gigabytes and going all the way up gigabytes per module. Now, to store the relational data, we have used SSDs. We have used SATA SSDs for storing the data. We have used 2 different hard drive SSD capacities, being 800 GB as well as 80 gigabytes. Now, the testing that we have done and the memhive actually runs on Linux. Memhive on Fedora Core 31 Linux. The PMDK version we have used is 1.7. The memhive is actually a Postgres variant. That means the Postgres at version 12 has been taken, and then the features on top of that is actually called memhive. So the base version that we have tested memhive against is the Postgres version 12, which is the currently available. The file system that we have used is ext4. Yeah. Next slide. In order to test, databases, benchmarks that have been proposed by TPC, we have used 2 such benchmarks to actually clearly categorize 2 different workloads. One being OLAP, the other one being OLTP. So online analytical processing is actually tested with a test specification called TPC-H. And DBT3 is a tool which actually from TPC. So DBT3 tool has various options to vary the database sizes, the streams, and all that, which is as part of the TPC-H specification. In our test with DBT3, we have used database sizes which is ranging from 32 gigabytes to 230 gigabytes. The number of streams have been varied from 1 to 15. Talking about in the next slides. The other benchmark is called the TPC-B. We have used PGBench, which is a popular Postgres benchmark tool, which is a TPC-B-like implementation, and that comes along with Postgres itself. So we have used this PGBench for doing the OLTP benchmarking. Used a fixed size of 350 gigabytes in this case, and then varied the number of clients from 5 to 40. And we have used the standard time for the test at 30 minutes for the various tests that we have done. The second thing which is mentioned here is the tests that are bound to one socket using NumaCTL. So all the tests that we've done are performed with only one of the sockets that is available in the server. So that means we are left with 128 gigabytes times 6 PMEM modules, which are actually configured in an interleaved mode. And then one of the processors is being used. And then again, the DRAM as well is restricted to 6 modules. So here's a comparison of the various things that could change between when we actually compare the standard Postgres with memhive Postgres. So obviously the hallmark feature of memhive will be the persistent cache. So the Optin persistent cache is actually configured as 400 gigabytes, and that is being one of the things in memhive Postgres standard version. The DRAM capacities used are the same in both the cases. The wall is actually kept on SSD in case of standard Postgres, whereas it's placed in persistent memory in FSTAX mode in case of memhive Postgres. The relation data we would want always to be in the SSDs. So both the standard Postgres as well as memhive Postgres place the relation. Now the shared buffers is going to be continuing to be in DRAM in case of standard Postgres, whereas it is using the Optin persistent cache in case of Postgres SQL. So these are the different parameters in which the changes have been done for comparison. All right, so here we can see the results that I was talking about with the various benchmarks. The first one we are seeing here is the TPC-H online analytical processing benchmark. So one of the metrics that the TPC-H provides is something called the query processing power. So the query processing power is a metric which tells how fast a system can actually respond to a single stream of where the queries are being issued from. So in this case, the stream is going to be only one. So that means only one client is issuing queries, one in a sequential manner, one after the other. And then called QPP, which actually determines how good the processing engine is. So you can see here that we have run the test against different database sizes, which as you can see on the x-axis. So we have ranged that from 32 gigabytes to 230 gigabytes. And you can see the QPP number, which shows how good the performances of the database is. So the higher the number, the better it is in this case. The first data point that you see here, the standard database Postgres v12 is actually outperforming the memhive. Why is this the case? This is because of the 90 gigabytes of RAM that actually fit into the RAM. As you see that the database size increases, the RAM is limited, and hence it starts performing lower and lower. But since we have a persistent cache which can actually scale to really large sizes, we can see that at the 230 gigabyte size, you can almost see there is a 5x the performance with respect to the QPP with the MemHive. Next. So the another metric that the TPCH specification provides is called the throughput numerical quantity, or TNQ. This TNQ is a number which is obtained with multiple streams, right? So we have a fixed size database, but we vary the streams in this case. So you can see that the x-axis is actually the stream count being varied. We have started from only one stream and then went on till 15 streams. This graph clearly shows that there is a tremendous capability of persistent memory with respect to parallelism. So as the number of streams increase, we can clearly see that persistent memory is able to cater to that different streams hitting the database in parallel. Now, even in this case, higher the number that you see on the graph, the better the throughput. We can clearly see that standard Postgres is actually deteriorating as the stream increases, whereas MemHive is able to scale into really good numbers, even with next. Okay, now let's look at the OLTP benchmarks, which is the TPCB, which I was talking about. We've used PGBench tool, as I mentioned earlier. And here the metric is transactions per second. So PGBench gives the transactions per second when we run with various parameters, the various the workload. What we are seeing here is the read-only transactions or select only. That means the clients issue only select queries, only reads into the database. On the x-axis, we can see that we have varied the number of clients from 5 to 40. And if you remember, we have used a fixed size database here, which is 350 gigabytes. So as we can see that the transactions can keep increasing in case of MemHive with persistent memory. This is because the persistent memory cache that we have built in MemHive is actually keeping the entire database in the cache. It's really warm, and any query that comes in is served in a really fast manner. And hence the number of transactions, the transactions per second number is really high. It is up to 15x in the case where it's in the OLTP case. Next. So here we can look at another metric from PGBench, which is again transactions per second, but this time it is a mixed workload, or we have selects as well as updates and inserts happening in a transaction. So the number of transactions per second here denotes one transaction having multiple things happening inside the transaction. That is selects, then updates, and then inserts. So again, we have varied the number of clients to see how the scaling happens with respect to MemHive, which has placed its wall on the memory in FSTax mode. So we can clearly see that with clients being 40, the MemHive is able to achieve up to 3.5x of the regular standard Postgres v12. Next. Okay. So the primary aim of using persistent memory is to reduce the DRAM footprint, right? Really speaking. So the aim is to reduce the DRAM to a minimum and have more persistent memory to actually help scale it vertically. So here's an interesting slide which shows that even if we reduce the DRAM to 32 gigabytes, we can clearly see that the performance that is provided by MemHive with persistent memory is really close to what we have seen with the benchmarks that we have just seen in the previous slides, which was having 90 gigabytes in the tests. So even if we reduce the DRAM, the persistent cache is actually providing such a good advantage that it is not reducing the transactions per second at all. We can clearly see that both the read-only transactions per second and read-write both are very similar to the previous test that we have done. Next. So here is a quick summary of what I've shown in the previous slides. Improvement in the read part of the database queries. In case of both OLAP as well as OLTP, we can see up to 10x the throughput and 15x. The OLAP is mostly read-only, so hence we can clearly see that there has been a tremendous increase in the performance as the parallelism increases as well. So both OLTP and OLAP have reached up to 15x, 10x respectively in their transactions per second. Been 3.5x of the regular Postgres. The impact of flush and drains that carries with the that is very important in case of persistent memory is quite negligible. Even if you have flush and drain, it's just varying the performance only by 2 or 3%. So that means to say, if you don't actually want the store to be consistent across reboots or something like that, that is also possible, but that could give you just 2 or 3% extra benefit. That's about it. Next. Okay, so here are the conclusions from various things that we have talked about today. First things is, let us talk about the conclusions that we have drawn with persistent memory being used as a Postgres persistent cache. So if you want to have a lot of your database coming out of warm or really close to the memory speeds, you could use a persistent cache from Memhive, and it scales linearly as you can keep adding more memory or persistent memory into the server. So the DRAM has a limit of, let's say, 700 gigabytes, but persistent memory can reach terabytes in this particular area, and hence, the bigger the database size, and the larger the will always keep scaling vertically. So that is really ideal to have in this case. Let's say your database always fits into memory, but it's actually big compared to the DRAM that you have. Again, persistent cache into your database into an in-memory database, Postgres into in-memory, because it all fits the entire database pages into the persistent cache. One of the most important advantages of using persistent cache is that it's not just a cache which is warm, it's also persistent, right? So that means across reboots and restarts of Postgres, it is always going to be warm. So your time to get the maximum out of the queries, that means when you start Postgres, it's already the queries are super fast starting from the first query. Like I mentioned earlier, in order to reduce the cost, the DRAM is much more expensive compared to persistent memory, especially Intel Optin, if we consider $1 per gigabyte. So when the aim is to reduce DRAM, automatically the cost also reduces. So that means this is actually a replacement for DRAM in case of for accommodating large databases into memory. Let's say the persistent cache also has this advantage that there is no redundancy required. And if there is, let's say, a failure or there is a corruption or something like that, the persistent cache and just rebuild it from scratch. And hence, there is no extra cost that is involved, or there is no extra need for building redundancy for the persistent cache itself. Next. Okay, so for the data part of it, persistent memory is very ideal for storing stuff like wall, the actual relational database, as well as index. In case we would want redundancy, then we would go for the persistent memory mode, which is called sector mode. In that case, sector mode is able to provide us with a volume utilized for building LVM related redundancy, either mirror or RAID or any such things. Let's say we don't want any kind of redundancy, but we are purely concentrating on the performance. In that case, we could place the Postgres data as well as index files on the persistent memory as well, which would give really significant benefits by having the speed as well as scalability. What else would I? So again, the FSDAX mode for cache has been used. That means if there is any failure with respect to persistent memory DIMM, we would always have the option of rebuilding the cache, and hence there would be no disruption or loss of data at all when using the persistent cache. All right. Okay, so that's about the conclusion and the things that we wanted to talk today. Here is how you would reach us. If you're interested, you could always look at our site memhive.io or write to us at info@memhive.io for a free trial of Memhive as well from our website, where we have a form which you could just fill up, and then we'll be able to gladly help you with a free trial and help you see how the benefit of persistent memory can be used with Memhive SQL server. Thank you very much. That's it. Naresh, do you have anything else to say?
For listening to this presentation.
All right. Thank you very much.